So something new, solving systems of linear equations. So this time what we're looking at are more than one equation at a time. So first of all, before we get into those, the solution to an equation is a value for the variable that makes the equation true, that makes the left side equal to the right side. So for the simple equation x plus 3 equals 8, our solution is x equals 5, because if we're to put 5 into the equation in place of the variable, we get a true statement. 5 plus 3 does equal 8. It's x equal 5 is the solution because it makes the equation true. When we've got a system of equations such as this, we have more than one variable and more than one equation. We're going to only look at systems with two equations and two variables. There are larger equations with more variables, but we won't cover those in this class. In this case, the solution to the system of equations are values of the variables, a value for x and a value for y, that make both equations true. In this particular example, 2, 3, shorthand for x equals 2 and y equals 3 is the solution, because if we put them into the first equation, x plus y equals 5, x is replaced with 2, y is replaced with 3. That gives us 2 plus 3 equals 5. So that satisfies the first equation. The second equation is x subtract y equals negative 1. So x is 2, subtract y is 3. 2 subtract 3 does in fact equal negative 1, so we know the second equation is also satisfied. So the solution to the equation is not just one number. It takes two numbers, 2, 3, or x equals 2, y equals 3, to write the solution, the one solution to the system. Okay, finding these, we're going to go through three different methods for finding solutions. The first one we're going to look at is solving by graphing. This one's the most intuitive. It's visual. A lot of us are visual people. And what we're going to do is look for the point of intersection. So that's the one point that they have in common. And that one point is the solution to both the equations. So if we have y equals 3 subtract x, we can graph that. So here our y-intercept is 3. Our slope is negative 1, so down 1 over 1, down 1 over 1, down 1 over 1. We'll get a few points here just because I'm not very good at drawing straight lines. Give me something to aim for. And then our second equation, y equals x subtract 1, so our y-intercept is negative 1. And here our slope is positive 1. Up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. And I think you can probably see the solution. So the point they have in common is right here. And at that point, it has coordinates 2, 1, which is x equals 2 and y equals 1. If we take that and check in both equations, so when y is 1 and x is 2, is this true? Does 1 equal 3 subtract 2? Yes, it does. Checking the second equation, y equals x subtract 1. Again, letting y be 1 equals x, which is 2, subtract 1. Does 1 equal 2 subtract 1? Yes, it does. And so we have our solution to the equation. Here's another one. This one will take a little more work just because we're not in slope-intercept form. But remember, there's a nice way to graph these when they're in this standard form, ax plus by equals c, and that's by finding the intercepts. So taking the first equation here, make a little table of values. So first what we're going to do is let x equals 0, and that would leave us with negative 4y equals 20. Dividing by negative 4 would give us y equals negative 5, so there's our y-intercept. Then if we let y equals 0, we're left with 5x equals 20. Dividing by 5 gives us x equals 4, and we've got our x and y intercepts. So when x is 0, y is negative 5. And when x is 4, y is 0. There's our y-intercept. And we've got our first line. And taking the second one, second equation here, if we let x equals 0, that leaves us with 4y equals negative 4. Dividing by 4 gives us y is negative 1. Letting y be 0, That gives us negative x equals negative 4. Dividing by negative 1 gives us x equals positive 4. So the y-intercept, 0, negative 1. And the x-intercept is 4, 0. And that makes things easy because they're crossing right there at the x-intercept. So our solution to both equations is the point 4, 0. Or you can write it out as x equals 4, y equals 0. Again, it takes two numbers to make the one solution. Okay. Both of these examples have had one solution. Think a minute, what would be a system that would not have a solution? Or when would two lines not have a point of intersection? Would you like a hint? Yes, you have two parallel lines. The two lines will not cross. There'll be no point in common, and there'll be no solution to the system. I have a special case to think about. Could a system have more than one solution? So if you've got a straight line, is there a way another straight line could touch it in more than one point? Now, if we had another function that wasn't a straight line, like such as a parabola, we could get 2 points of intersection, have two solutions. We'll talk about those in Math 111. We're not going to talk about that in this class, so don't worry about it. But if we've got a straight line, and if we had another straight line, is there any way you could touch it in more than one point? And actually, there is another way you can touch it more than one point, and that would be at the second line, was right on top of the first line. Then they would actually have an infinite number of points in common. And so that's going to be our second special case. When two lines are both the same line, then we're going to have an infinite number of solutions. Okay, so that's a nice, graphically, it's a nice way to look at these to get started. Oh, that's right, got another example here for you. Sorry. Let's graph both of these. They're in the intercept form, they're in the standard form, so we'll graph them using intercepts. So taking the first equation here, and let me get a skinnier line here, right with. So if x is 0, that would simply leave me with y equals 5. And then if y is 0, I'll have 2x equals 5, which would give me x equals 5 halves. And then taking this one, if I let x equal 0, that leaves me with 2y equals 10. If 2y equals 10, then y equals 5. And if I let y be 0, I'm left with 4x equals 10, which gives me x equals 10 over 4 or 5 over 2. So these two equations are identical. When we graph them, 0, 5, and 2.5, 0, they're both the same line. And so this would be a situation where we've got an infinite number of points in common, and we can simply say that the solution is an infinite number of values. Okay, now when you're doing your homework in the book and you check your answers, you're not going to see this in the back of the book. What you're going to see in the back of the book is actually something called set notation. And it's going to say the set of all x and y coordinates such that 2x plus y is equal to 5. So they're saying the solution is all points on this line, which is fine. But in Math 95, we're not going to require you to write that out. You can simply say infinite number of solutions and stop there. When we get into Math 111, then I'm going to make you start writing things like this out for infinite number of solutions for that special case. Okay, so one other, I think this one's also a special case. To graph both of these, how about just word change of pace? I'm going to rewrite these in slope-intercept form. So I'll subtract the x to the other side, gives me negative y equals negative x plus 1. Dividing by negative 1 would give me y equals x subtract 1 for my first equation. In this one, if I solve for y to get it in slope-intercept form, I'll add x to both sides, and that gives me y equals x plus 3. So let's graph this one first. I have a y-intercept of negative 1 and a slope of 1. So up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. And there's my first line. My second one here, I've got a y-intercept of 3, 1, 2, 3. And my slope again is 1. So up 1 over 1, up 1 over 1, up 1 over 1. We've got two parallel lines. They'll never cross, they'll never intersect, there's no point in common, so there's no solution in common, and we simply say there is no solution to this system of equations. Okay, so the graphing method works great as long as the answer is nice, as long as they cross at two nice points or clearly parallel or clearly the same line. But we need an algebraic method of solving also, and there's actually two of them. And this works nice if the answer, say, is x is 5/3 and y is 7/9. That's really hard to read off of a graph, but we can find it algebraically. So of our two methods, the first one, solving by substitution, is the most intuitive, so it's usually the easier one to pick up at first, though I think the second method is a little harder to get used to, but is actually a little more efficient. So try them both, see what you like. So solving a system by substitution, the idea is to solve one of the equations for one of the variables and substitute the result into the other equation. So always take the simplest path possible. Look for an x or y that would be easy to solve for. In this equation, it would be very easy to solve for x or for y. I could simply subtract the y to the other side and say x is 4 subtract y. And then I'm going to take this, substitute it into the other equation in place of the x. So 2 times x subtract y equals negative 1, and then I'm replacing the x with 4 subtract y. Now I've got an equation that has only one type of variable in it, and I can solve this. So I can distribute here, and I'll get 8 subtract 2y, subtract 1y equals negative 1. I've got some like terms here, so that would give me 8 subtract 3y is negative 1. Subtracting the 8 to get the non-variables together, constants together, gives me negative 3y equals negative 9. Dividing by negative 3, and I get y equals 3. Am I done? No, because it takes two numbers to make one solution. I've found the y coordinate, but I also need to find the x coordinate. Once I've got this, though, I can go back to the original problem, take either of the two equations, say the x plus y equals 4. I now know that y is 3, so I can put 3 in for y, and now solve for x. And so my solution is x is 1 and y is 3. That was not what I meant to write. Let me clean that up there. Okay, x is 1, y is 3. And that's my solution to the equation. Okay, let me do one more, and then I'm going to leave the third one here for you to do as part of your pre-class assignment. So solving by substitution, looking at this one here, I'm going to take the second equation, solve for x, because that one doesn't have a coefficient. Well, it's got an understood coefficient of 1, but it's really easy to solve for x without dividing. I don't have to worry about running into any fractions. So if I solve the second equation for x, I can add 2y to both sides, and I get x equals 2y subtract 4. And I'll take this, substitute it into the first equation, again in place of x. So 2x plus 3y equals 6. And then I'm replacing the x with the 2y subtract 4. Then again, I got an equation that only has y's, so I can solve. So first I'll distribute the 2 through. I'll get 4y subtract 8 plus 3y equals 6. Combining like terms, 7y subtract 8 equals 6. Adding 8 to both sides, I get 7y equals 14, and so y equals 2. I'm halfway there. Then I need to go back and find the x, so I can go to either of the two equations. I think I'll take the second one, a little less complicated. X subtract 2y is negative 4, and I'll replace the y with the value I found for y, and solve. And I get x equals 0. So it takes these two numbers to make my one solution. X is 0, y is 2. Okay, so I want you to take this next one, and you do that one as part of your pre-class assignment to hand in at the next class. Third method, again, this one's a little harder to catch on to, but is actually a little easier to do. It's called solving by elimination. It's also called solving by the combination method in other books. And what we want to do is eliminate one of the variables. When we start off with the system, we have two equations and two variables, x's and y's. And the idea is to multiply one or both of the equations by a number so that the coefficients of one of the variables are opposites of each other. Then add the two equations together to eliminate one of the variables. So my first example here is quite nice because I can simply take both of these two equations, add them together, and because I have a positive 1y and a negative 1y, the y's are going to cancel each other out and eliminate the y, leaving me with an equation that has only one variable. So 1x plus 2x is 3x. Y subtract y is 0, so it's gone. And 4 plus negative 1 is 3. This I can solve for x. Now that I know my x value, I can go back and find my y value. If x plus y is 4, but x is 1, then subtracting 1, y has to be 3. And I found my solution. X is 1, y is 3. Let's see, do I have another example down here? Must be on the next page. Okay, this one's a little harder. It doesn't just fall out. We've got to think a little bit here. So again, the idea is to have the coefficients for one of the variables to be the same, only one positive and one negative. Got a strange little mark there. That's supposed to be a 6x, not a 16x there. What I want to do this time is I'm going to take the first equation and I'm going to multiply it by negative 6. The reason I'm going to multiply the equation by negative 6 is that I'll have a negative 6x, which will cancel with my positive 6x. I also could multiply by negative 4 to get a negative 4y, which would cancel with my positive 4y. So it can be a little confusing here as there are multiple correct ways to do the problem. But let's just eliminate the x's. So if I multiply the first equation by negative 6, that turns into negative 6x plus negative 6y equals negative 36. So be careful. It's really easy to forget to multiply the right side of the equation. The second equation, I can just take it as it is, 6x plus 4y equals 20. And now when I add the two equations together, my x's are going to cancel out. Negative 6y plus 4y is negative 2y. Negative 36 plus 20 is negative 16. Divide both sides by negative 2, I get y equals 8. And again, I'm only halfway done. I need to go back, the original problem. Taking the first equation, x plus y is 6. Substitute in my 8. Solving, subtracting 8 gives me x equals negative 2. And so my solution is negative 2, 8. And again, I could have done the exact same thing, but instead of eliminating x, I could eliminate y. So here's the original system. If I multiply the first equation by a negative 4, I'll get negative 4x plus negative 4y equals negative 24. Combining 6x subtract 4x would be 2x. 4y plus negative 4y is 0, so the y's are gone. 20 plus negative 24 is negative 4. Dividing by 2, I get x equals negative 2. Once I've got my x value, I can go back to either of the two original equations. I'll take the more complicated one this time. 6x plus 4y equals 20. I'll put my negative 2 in for x and solve for y. Oops, plus 4y equals 20. And add 12 to both sides, I get 4y equals 32, sorry. Dividing by 4, y equals 8. And again, the solution, negative 2, positive 8. So there are multiple correct approaches you can use when you're solving by the combination method. Okay, we'll run through this one. This one, I think, might give us one of our special cases. So if I want to eliminate the x's here, I could multiply the first equation by negative 2. That way, my 2x times negative 2 would be a negative 4x, and the 4x and the negative 4x would cancel out. So my goal is to try to get the coefficients for the x's or the coefficients for the y's to be the same value, but one positive, one negative. So negative 2 times 2x is negative 4x. Negative 2 times y is negative 2y. 2 times negative 2 is negative 4. So 4x subtract 4x is 0. 2y subtract 2y is 0. And 4 subtract 4 is 0. Okay, important question here. Does 0 equal 0? I hope your answer is yes. Okay, everything eliminated. This indicates we've got one of our special cases, but we did end up with something that was true. 0 does equal 0. So of our two special cases, this is not the no solution. What we really have here is a case where both lines are the same. Both of these equations are identical to each other once you do a little simplifying. And so what we have is a situation where we were going to have an infinite number of solutions. If we had gone through here and ended up with something that didn't make sense, say something like 0 equals 2, which is not true, then that would indicate we had the no solution situation.